What is stray current? Imagine electricity as a dedicated workforce, diligently following the wires and components laid out for its specific tasks within an electrical system. However, sometimes, a portion of this workforce, known as stray current, deviates from its intended path. Instead of confining itself to the insulated pathways designed for it, this errant electricity finds alternative routes, often through the earth itself or other conductive materials that happen to be nearby. This phenomenon of stray current is particularly prevalent in direct current, DC, power systems. Think of the bustling network of electric trains, trams, and metros that power our cities. These systems often utilize the rails as a return pathway for the electrical current that propels the vehicles. However, due to imperfections in insulation or breaks in the continuity of the rail lines, a portion of this current can leak out and find its way into the surrounding ground and nearby metallic structures. To prevent this unwanted leakage, a crucial strategy involves minimizing the resistance of the intended return path. By providing a clear and low-resistance route back to the source, the electricity is more likely to follow this preferred path rather than venturing into unintended areas. This is akin to ensuring a smooth and wide highway for traffic, reducing the likelihood of vehicles veering off onto side roads. The extent to which stray current can increase from an electrical circuit to a neighboring structure is directly related to the voltage potential present at a given point within that circuit. A higher voltage potential creates a stronger push for the current, making it more likely to seek alternative routes if the intended path offers significant resistance. Therefore, effectively reducing the resistance within the return circuit is a key method for mitigating the problem of stray currents. Detecting the presence of stray current often involves the use of a multimeter, a versatile electrical testing instrument. By carefully measuring the amperage, or the rate of electrical current flow, between a designated bonding system wire and any through-hole metallic components, technicians can identify potential stray current issues. A current reading approaching or exceeding 1 mA is generally considered a warning sign, indicating an excessive amount of stray current flow. This level of unintended current can be sufficient to cause detrimental effects over time, particularly in the form of corrosion. To pinpoint the specific source of a detected stray current, a systematic process of elimination is often employed. This involves turning off individual circuit breakers one by one while continuously monitoring the current flow. When the stray current reading drops significantly after a particular circuit breaker is switched off, it indicates that the fault likely lies within that specific circuit or the equipment connected to it. Furthermore, it's important to check for stray current under various operating conditions, including when the system is connected to shore power. Shore power, an external electrical supply often used by boats and other mobile systems, can sometimes introduce or exacerbate stray current problems. The effects of stray current can be quite damaging, extending beyond just electrical systems. One significant consequence is the corrosion of reinforced concrete structures. The unintended flow of electricity can interact with the moisture and chemical compounds within the concrete, accelerating the breakdown of the reinforcing steel bars embedded within. Interestingly, stray currents can also contribute to the corrosion of cement-based materials even when not directly involving reinforcing steel. When combined with other environmental factors, such as a humid environment and the presence of groundwater flow, the passage of stray current can weaken the structural integrity of these materials, as seen in subway systems. Stray current discharge is a specific scenario where a machine's normal electrical current potential finds an abnormal pathway to the earth. This often occurs due to an unintended electrical connection or fault within the machine. A common example of stray current discharge is seen in diesel-powered generators where the armature, a rotating component carrying electrical current, inadvertently earths out through the engine's crankshaft bearings. This abnormal pathway is often created when the engine ingests hard particles large enough to breach the normal insulating barriers. Whether dealing with direct current, DC, alternating current, AC, or even high-frequency pulses, stray electric currents have a tendency to find their way into motor bearings. These critical components, designed for smooth mechanical rotation, can suffer significant damage when subjected to the passage of unintended electrical current. When stray electric currents flow through a bearing, they can cause a range of detrimental effects. This includes the formation of microscopic craters on the bearing raceway, the melting of metal surfaces due to localized heating, and the degradation of the lubricant that is essential for reducing friction and wear. To proactively prevent stray current corrosion in steel structures, a technique involving sacrificial anodes is often employed. These anodes are typically made of a more electrochemically active metal, such as zinc, which readily corrodes in preference to the steel. When a sacrificial anode is electrically connected to a water-based steel structure, it becomes the new path of least resistance for any stray currents present. As a result, the stray current preferentially flows through the zinc anode, causing it to corrode while protecting the steel structure from damage. The root causes of stray current often lie in imbalances within the electrical supply system or flaws in the wiring. These imperfections can create unintended electrical potentials between objects that should ideally not be subjected to any voltage difference. This existence of unintended electrical potential can lead to current flow through buildings, the ground, or interconnected equipment, effectively bypassing the designed electrical circuits. To address the challenges posed by stray current, specialized stray current monitoring systems, SCMS, have been developed. These systems are designed to continuously monitor electrical equipment for the presence of stray current, providing an early warning of potential corrosion damage. Modern SCMS, such as those offered by Sachiran, are often compliant with international standards like EN 50122-2/2011. These sophisticated systems offer comprehensive capabilities for analysis, real-time display of current levels, alarm signaling when thresholds are exceeded, and detailed logging of historical data for trend analysis. Stray current interference describes a situation where current flowing through an electrolyte, such as soil or water, originates from metal conductors within these media due to electrical installations. This interference can be caused by both direct current, DC, and alternating current, AC, often at common power frequencies like 50 Hz or a related frequency like 50 Hz. Resolving stray voltage problems, which can be a precursor to stray current, involves addressing the underlying causes of the unintended electrical potential. This can include rectifying faulty neutral connections, removing or repairing malfunctioning electrical loads, and improving or correcting deficiencies in the electrical wiring and grounding systems. Furthermore, balancing the electrical load across different phases in a system and controlling leakage current through measures like cleaning, re-insulating, or properly grounding equipment can significantly reduce stray voltage and the potential for stray current flow. The measurement of stray currents typically involves the use of self-recording voltmeters. Since the electrical potential differences associated with stray currents are often relatively small, it is essential to utilize measuring devices with a high input impedance, typically a minimum of 0.1 mΩ/V, to ensure accurate readings and minimize the impact of the measuring device on the circuit being tested. In conclusion, stray current represents an unintended flow of electricity outside of its designated pathways. Understanding its sources, detection methods, and detrimental effects, particularly the corrosion of metallic and concrete structures, is paramount. Implementing appropriate prevention and mitigation strategies, along with continuous monitoring, is crucial for ensuring the safety, reliability, and longevity of electrical systems and the infrastructure they support.